So starting with very initials, we are talking about deep learning over here. And as we know that deep learning, this is one of the most revolutionizing trend in your artificial intelligence domain. And the main idea behind using this deep learning concept is to interact with complex data sets, in that maybe in the form of images and your videos more preferably. These are the most common type of data sets, although many other informations are also there, like we have NLP, that is your natural language processing, that is also part of this domain. So plenty of details, but we start with generally with images and videos out there to work on deep learning. And in deep learning, basically, the inspiration itself is taken from neural networks. So anyone who has a little bit basic idea about ANN, artificial neural network, or a simple neural network concept that we call it, then you can easily understand how deep learning may be working, because the inspiration is taken from there only. The idea is to understand how human brain works, and that is basically mimicked into a machine by using a simple layer connection, or multiple layers that are arranged one after another to do the same parallel processing, same as human brain. That is basically the initial concept of neural networks, and then we further extend it to the deep learning also. So we generally call it a sub branch of machine learning. You will see AI as the main universe, inside which we have machine learning, and as a further deeper concept in that we have is deep learning. That is a subset of artificial intelligence, basically, and it is trying to imitate the behavior of human brain itself. So let us first get a quick idea how human brain works. Just a quick update I'll give you. We learn from experiences generally. With a layman level understanding, you'll understand this. So generally in human brain we process information by just seeing, by getting experience, by getting exposed day to day with different data points or different kind of visualizations around us, and that adds some value to our knowledge, and accordingly we make some decisions. So there is a continuous learning process that helps us to make certain decisions in different scenarios, and every human being may have a different life perspective based on what they have learned throughout their life, that we can all agree to. So here also what we are doing is we are simply connecting that human brain process to a machine level learning by mimicking that behavior. What we are trying to do is we are adding multiple layers in such a manner that they can extract information from the field data, or maybe image data, or maybe video data, and they can help us to make certain decisions same as human brain. The main difference is human brain is trained on several aspects. It can make decision on wide range of topics, but when we talk about a deep learning model, it is mainly trained on a specific task. It can execute, it can perform computations on a specific task, but however it can handle very complex computations in a very faster manner, since we are taking help from machines to do that computation part. So layer by layer, several connections we are making, and we are transferring information further. These deep learning models are capable enough to extract features from your dataset. In last two sessions, we have discussed about different data analysis approaches, data cleaning approaches, and then visualization approaches. They are mainly required or more commonly used when we are dealing with small data sets, or that are useful in case of simple data science and machine learning operations. Majority of those applications are relevant to your machine learning based developments, but still we need to understand the concept from there, because that is definitely going to help you further in hyper tuning your deep learning models, in understanding your data set, and in visualizing deeper information about your different data sets. Because sometimes we get data set in the form of CSV files, sometimes we get in the form of image or videos. Several options are there. So once you learn the stats behind data, you can understand meaning of every type of data that you have in hand. So in case of deep learning, we mainly prefer using very high resolution data sets that include images and videos that as I discussed. So we generally call it a big data. Very extensive memory these kind of data sets require. Even sometimes we have a very huge CSV file that may not be compatible with a basic machine learning model, and we need a deep learning model to process it. Like when you have maybe 50 lakhs observations or crores of observations obtained from certain environment, and a deep learning model find it very huge to process, a machine learning model finds it very huge to process. So we can switch again to deep learning with CSV datasets also. That is also a possibility. In general, this is the layer by layer abstraction we get from a deep learning model. We apply, for instance, here I'm taking just a simple example of facial images that I'm inserting on the input side of your deep learning model. Just a quick overview we are getting from here. So it will first try to extract the local contrast of the images, like where are the different brightness levels or initial features, initial information about how the contrast levels are changing, how the darker and brighter pixels are appearing in your image. Then on the next layer, possibly it will extract your specific facial features that may include extraction of maybe your nose area, your eye area, lip area, or any specific features that at a simple level it can extract. Then further, there may be multiple layers further. We are just showing a very small architecture over here, just two hidden layers I have added. Generally in deep learning, we have like hundreds or thousands of hidden layers inside. There is like a black box, we have a number of layers we can have inside, depending upon what type of model we are using, how we are using layer by layer successive connections out there. So this is just a generalized idea. So on the next level, maybe more deeper features it will get, the maybe the skin tones, or even maybe the information about how different angles of your face are appearing for different images that we are getting. And by extracting this level by level information, ultimately we are getting it to the output layer that will finally make decision to recognize a specific face from the training data set. Like maybe we have just an example we can take, like this kind of model. Maybe you have trained for certain specific scenario, like maybe for an industrial application or for a specific company, where you have trained a model to recognize all its employees. So the gate will open only when the face of a authorized person or authorized employee will be identified on the security gate. So that feature we can add into your CCTV system. We can create a high-end security system over there with this facial recognition, so that in a specific area where only authenticated people are allowed to go, that we can track with the help of face directly. So what we'll do is we'll train a deep learning model out there to detect specific authorized faces, and when it is able to match those features, then only it will permit access to that area. Otherwise, it will say not allowed, or anything we can add to our system accordingly. So while building this entire process, the simple technique is layer by layer abstraction. Like I already discussed, the input layer will first get the local contrast information like colors, luminosity, etc. Then first hidden layer will get specific features, eyes, nose, etc. The next layer may try to determine correct face. This is just a quicker level understanding we are having. Otherwise, there will be hundreds of layers. Each one of them will extract little relevance from the faces, and then that information will be compiled by the end to get the final information about a specific face. Because for a deep learning model, even within a single face, there will be like thousands of the different features that it will extract about everything that we have on the face. Every single spot it will recognize while scanning your face. So basically, as we increase hidden layers inside deep learning model, it is able to solve more complex problems because it is able to extract more deeper information from the provided data set based on that. And on this deep learning concept, one of the most basic network we have is your convolution neural network that we precisely call CNN, one of the most basic network that we have. So let us get a quick idea about how this CNN works. I'll just give a quick reference of this to you. So convolution neural network that we also call a ConvNet sometime with a nickname. This is basically designed for some image classification, detection, recognition, or segmentation task. Those are the common applications of a CNN model. This generally works on some basic applications, although there are several modified versions of CNN also that you will find in different literature surveys, and they are being implemented for many other applications as well. So in the practical scenarios, you will find them in security cameras, in autonomous vehicles and systems. One such example I have just given you with CCTV camera information. We can track from there itself for the authorization purpose in a specific company. Or this can be used at your home as well. Like if any unauthorized person tries to enter your home, the security system will be locked because the face will not be detected as authorized one. So CNNs are generally inspired from the ANN interface only that I have discussed already. So I'm not going to repeat this in detail. What we say generally when we talk about machine learning algorithms, they are basically some statistical and mathematical models. In machine learning, majority of your models are statistical or mathematical models. They simply follow like some tree-based structures or some grid-based structures there are, and SVMs we have with some space organizations for different patterns of data. And the main requirement in case of machine learning is to apply some manual efforts to clean your data that we have seen already in last 2 days. We need to clean a data first, we need to pre-process the data first, we need to understand its pattern, we need to do manual feature engineering to make a data set ready for a machine learning model. That is the enhanced process in case of machine learning. And we spend a lot of time on the cleaning part only, then we build a model. But the technique is different in case of deep learning or in CNN specifically. In this case, we have several layers within the model itself, and every layer is able to process the raw data directly. We need not to do any pre-processing. There are very rarely any pre-processing required. In some cases only, like if sometime we have some artifacts in your images, or maybe like some names, or some maybe you are getting some MRI images where patient names are printed on the MRI. So maybe you just have to remove those names for the safety purpose or for the essential easy recognition. So those type of things sometimes we have to do, like maybe patient IDs we may have to remove from that MRI, or tumor scans. So those things sometimes we have to do as a part of your cleaning process. Otherwise, majority of time a raw data goes well into a deep learning model, and we can extract relevant information layer after layer without requiring any manual process like machine learning models. So that is a benefit of deep learning. And in this case, you can have plenty of pre-trained architectures also, like in advanced age. Maybe some other experts in this course also may explain you some advanced models of this deep learning, like VGG16 we have, ResNet we have, Inception we have, and EfficientNet we have. These are advanced options we have with higher performance that can help you to train some complex data sets also easily. So, but when we talk about CNN, this is widely recognized for the image classification task because it has a versatile performance on that kind of things. Otherwise, sometimes we are also going to use it on speech recognition, etc., on time series analysis also. That also works fine. So, as an inspiration behind CNN, how we understand the layer-based abstraction, how we extract features, that is basically inspired from the human brain visual information processing. So you can compare these A and B images right here. This is how the work goes. This is just to understand the basic phenomena, because once you understand the basic phenomena, you will understand what layers are doing inside your system. Everything is inspired from the human brain. So if we take this first level, this upper one, what we are doing here basically, in the human brain, how the image is entering through our eyes, means our retina is scanning an image like this dog image, or maybe a scene where a dog is playing, that is being analyzed by your retina. What will happen next? Whenever a retina scans something, it will first send that information to LGN region. inside your brain. What is this LGN region? If we go into biological terms over there, this is basically a lateral geniculate nucleus that we have inside brain region that helps you to receive visual information from retina directly. So it will process this detail directly into your brain. And once it is processed like this, it will go into a specific region. And what is that region? Basically, we have a option available for visual area processing, and that we basically call, in terms of different regions, we call V1 region, V2 region, V3 region, V4 region. They also, we talk in terms of ventral streams that enter into the system, ventral streams for processing visual information. So you will see that in different sections of brain we have different V1, V2 and V4 are highlighted here. There is V3 region also that we have not highlighted right now here. So all of these are like layers of your CNN. In the brain also, we have different layers of feature extraction from that scene that we are seeing from your eyes directly, from the retina, whatever we are scanning. So step by step, your image will enter into different receptive fields. Like first it will go to the V1 region, then it will be some features will be extracted from that scene by V1 region. It will pass that information to V2 region, some features will be extracted over there as well. Then it will go to V3 region, it will go to V4 region, step by step, and ultimately it will go to the your IT region, that is inferior temporal cortex. So we call it IT region. That will help you to get impression, the final impression of your image, whatever we are processing through that. And accordingly, our brain will get signal about that entire scene, that whatever we are seeing, we are able to understand the process from that. This is what is happening inside human brain. The same we are trying to do with a CNN as well. On the CNN, we are trying to feed input or maybe a video frame, and from that scene we are doing level by level extraction. So there will be a input layer, maybe that works as your retina. The input layer will extract information at initial level. Then we have some convolution layers in the system. Then we have some pooling layers, and we have another pooling layer. There can be again hundreds of different layers. We can have some dense layers. These names we will discuss in detail also further. But this is the generalized process, and ultimately we are able to make decision about whatever we are looking at in this particular image through your CNN model. So exactly same process we are following. In human brain, we have billions of neurons to do this thing. Similarly, in case of CNN, we have billions of different layers, or we can say neurons also, in simple terms here. All the pixel values basically we have from every image, and they are being processed layer after layer to get the final outcome from your system out there. So in this CNN process, what we have is, there is a specific hierarchical structure that we are following based on the visual cortex of human brain, that are basically helping you to extract layer by layer information based on the features of the image. And ultimately we are representing that in the form of a matrix of pixels. So the idea is to establish first the local connectivity between different pixel values, same as human brain. So we'll try to see how one pixel may be related to other pixel, how the variation in the field is going on. All those things your system is going to extract. Similarly, we'll try to see the translation in variance in your those features, like how one feature is varying in a specific location in comparison to other location, and we pass some filters layer by layer to your stream of pixels that we are getting from the image scanning. And then based on that, we try to summarize local features from the image. Currently, we have used your CSV datasets. Features over there were in the form of your some column entries that we were getting. In case of CNN, the features are represented with the help of pixel values out there at initial level. And then we keep on doing some computations further, and we try to get the deeper details about the image based on those pixel values out there. That also we are going to discuss further. So there may be multiple feature maps that are created after every layer. Every layer is going to extract a new feature map based on how deeper it is getting with your layer. Sometimes we train a model with like 3 layers, then we train with 10 layers, then we train with 100 models, and we'll see how it is improving with higher number of layers. But generally, it is recommended that you should add minimum possible layers that are giving you good accuracy, because designing a model with very huge computational complexity is again going to require more CPU power, more computational complexity. It will consume more time also. So many factors will change based on design of your model. So best possible accuracy, if you are getting in lesser number of layers, that is definitely a good model, because you can deploy it anywhere in the field environment later on, like maybe on your cloud application, maybe on some of your websites, on maybe some of your mobile applications. If you have to deploy a model, it should be easier to carry on that processor. It should be not occupying too much memory. Sometimes we say that some application is going to take too much memory on your system when it runs, so we avoid to install such applications. So the same thing happens with the deep learning models also. How convenient models we are creating, how easy they are to deploy in the field environment, that thing we have to keep in mind always. Then while processing these CNN elements, we always add some non-linearity into the system. Most of the time there are several non-linear extractions we are doing from the feature maps that we get, and for that we apply some activation functions like ReLU, rectilinear function that we have. We'll discuss this also, the structure also further. So this is basically helping you to add non-linearity into data to extract the relevance of different pixel values out there, to establish relationship between those different bigger image candidates out there, and it will just help you to develop the final vision out of your model. So these are the key components of your CNN architecture. uh, a few layers I have added over here, although many of these layers we are going to discuss in detail tomorrow. Today we'll be just building one very basic model with the CNN architecture, where only the basic layers will be required. So it generally starts like we have one image of handwritten 2 over here. So layer by layer it will be processed. Like we have one convolution layer, we have max pooling layer, again we have convolution layer, again we have max pooling layer. There may be multiple of such combinations. Initial level we create like one convolution, one max pooling, one fully connected, and finally we may be getting output. But when we increase depth of your network, we may be adding multiple convolution layers, multiple pooling layers, so many things we can add based on how complex data set we are trying to handle. And we increase size of our model over there. Accordingly, it get deeper with the features out there. So what we may be doing in this entire process, let us get a quicker idea of this. Slide by slide we are applying some information. The very first thing, like this, we are getting this image on the input side. There may be a specific size of this image. 28 by 28 here represent your row and column matrix size, and 1 here represent your grayscale image. Sometimes we have RGB images. In that case, this 1 will be replaced by 3. That will be your depicting your RGB image. 1 here represents your grayscale image. So this is how we depict your metrics values out there. So in CNN, the very first thing we have is with your input layer, and we try to just extract relevant information based on the image applied to your model. For instance, if we have this as an input image, any size of this we can have, like 32 cross 32, 28 cross 28, 64 cross 64, any size of image you can have. So first we'll do some pixel representation for this particular thing. So there is a specific distribution for this. When I'm saying 32 cross 32, the this size will be 32 cross 32, the grid size basically, or the metric size we are saying. So generally what we say is that zeros represent one region and ones represent other region. So most preferably zeros represent your black regions and one represent your whiter region in your images. So what we do is, accordingly, information will be gathered on your system. So here, although this image I have added on the whiter background right now, but generally what we have is, like, if you have a black background here and over which a 2 with a brighter window is updated, so accordingly these pixel values will be updated. So zeros basically represent this black zone, and these values are depicting your 2, like this, something like this they might have decoded it. This is just a sample we have created. Otherwise it will be a full-fledged matrix that will depict this thing exactly, darker and whiter region with the pixel values. So depending upon how dark or how bright your pixel value is, accordingly a value inside this will be updated. This is how we establish relationship between an image and its pixel value. The darker and whiter regions ranging between 0 to 1, or on the wider scale it is generally 0 to the maximum range goes up to 255. So accordingly we can have the distribution for the RGB images also. So when we are processing this information, this is the initial image, and then this is the pixel representation of this particular image. When we process it further, first we will understand that the 0 weights are going to represent your black grids, and 1s are representing your white grids in a normal pattern. As a basic parameter we have this. Now one thing is, we'll first pass a kernel to process this information, a kernel of like this kind of matrix that we slide through your matrix, your pixel matrix, to extract layer by layer information. So first is your kernel on the this convolution layer. Now the first point is, when we design that kernel like a matrix of maybe 3 cross 3 to extract information from a matrix of 32 by 32, so we have to use this 3 cross 3 window and we have to slide it throughout the matrix to get the final information. But there has to be some specific weight elements inside this 3 cross 3 matrix, like here zeros and ones. These are the weight elements inside your kernel. So how we make decision about these weights? So these are basically developed during the training process. If any of you have already heard about ANN, you might have heard that some random weights are generated initially, and those weights are updated layer after layer after every epoch or after every iteration until we get the finest outcome from the extraction. Same is happening here also. We start with some random weight sequences, although we can control this also. We can use some optimization, we can control weights in the kernel also. But generally it starts with some random weight settings and we try to extract relevant information until and unless we are getting the best outcome. So we keep on updating weights from there during the training process. So what process will follow is, you will observe it here. This is, for instance, your pixel element that we are getting from the actual image. This is the kernel that I'm trying to convolve with this particular image. So this is the convolution sign we have over here. And this will help you to get a new matrix with little bit smaller size. How it gets smaller size matrix? For instance, if I compare it with this matrix and this example that I have over here. So this is like 1, 2, 3, 4, 5, 6 and 6 cross 6. We can see that kind of structure we have here with the grid size. So what we are doing here is, we are applying a 3 cross 3 kernel. So we start from the first section. 3 cross 3 will come along this. So we'll just put the filter or the kernel right here on the first position, and then we'll try to extract information by following a mathematical calculation out there. So what we'll do, see this one for the first place. Like for instance, these are the matrix values and these are the matrix values for the first level. So 0 into 1, you can see 0 into 1, then 0 into 0, 0 into 0, and then you have 0 multiplied by 1. This one, add, we are just summing up all the elements. So this will go ahead with all the elements, element wise convolution we are doing, and ultimately we are getting 0.1. So first element on the small scale matrix we are getting is 0.1. Similarly, then we decide about a window sliding function, whether we will slide it by 1 stride or 2 stride, means whether we will shift it next to this location, or whether we will shift it to this location by 1 or by 2, how the grid will be positioned in the next row. That setting we can apply on the model itself. So how deeper we want to enter into the model, accordingly the filter we will move. For instance, if we are moving it by 1, then next we'll do extraction on this particular portion. Then again we move it by 1, and then we'll do extraction on this particular, and ultimately we will do on this particular, and again downward also we will slide accordingly for step by step. So this is how ultimately we are getting this small set of pixel values by applying this calculation on all the filter slides. So this you get first level of convoluted matrix. In the similar manner, there will be unlimited layers that will help you to reduce size of the matrix with more exact features representing your image information. So even if there is a very big image that you are supplying with like maybe 28,000 into 28,000 pixel grid size, that will be further extracted with the help of kernel size of different values, and accordingly we are extracting relevant information from those layers out there. So with this sequence, what we are doing ultimately, we are extracting or we are detecting the abstract features from the model itself, and we will use it for different purpose. Depending upon how we are shifting your kernel, how we are using that kernel, how we are applying the mathematical formulas behind in the model, there are multiple settings that we can apply on the layers. It may be used for averaging the neighborhood. Sometimes we use it for subtracting the neighborhood, for the edge detection, or for blurring the image. Sometimes we are using it to get a better idea about the inherent features of your model. So all these things, depending upon how we are deploying your model, we can apply this information. So accordingly, what task we want to execute from the model, accordingly the techniques we are going to apply. Now, one more important part comes here is activation function. Generally, on the middle layers and input layers, we apply ReLU activation function, which has this shape. Those who might have gone with the basic ANN structure, they might have gone through several activation functions also. We have plenty of activation functions like linear activation function, softmax we have, and uh, many other options you will find, depending upon how we want to translate our information from the actual data to the next layer of data. So ReLU is one of the most commonly used input side function generally in your deep learning networks. And this is the architecture of ReLU, or the structure that we follow, or the mathematical equation. Max of 0 and z. So whatever is higher, whether z is higher or 0 is higher, accordingly the value will be updated. So for the negative values, definitely outcome will always be 0. For the positive values, it will follow the linear relation with the z. That is your rectilinear, or we can say your ReLU function. So this will help you to establish your convolution operation in much finer way, because we are extracting information layer by layer by using this particular relationship. This goes same as ANN. And when we have applied this, one more layer comes into role play, that is your pooling layer. I'm just giving a quick information on essential layers over here. I'll add more layers also tomorrow, and we'll build a deeper model also based on that. So the main goal of this pooling layer, this one again we use for reducing the dimension of the feature map. At the first layer, we use that with the convolution pattern. On the second level, we do the same thing by using pooling layer, but the mathematics behind this is going to be different. For instance, there are three different ways that we can use for the aggregation in case of pooling layer. We can have max pooling, we can have sum pooling, we can have average pooling. These are the most common terminologies you will find in research papers also, that what kind of pooling they have used. So as a beginner, we find it difficult to understand that what this max pooling may mean. This is basically a simple mathematical sequence that they are following. For instance, if this is the convoluted matrix that I'm getting from the previous layer, and I'm applying a max pooling with 2 cross 2 filter over it with a stride of 2. I hope all of you can understand it easily now. 2 cross 2 filter is the size will be like this, 2 cross 2. And stride 2 means I'll shift it by 2 elements. So first it will be applied on this, then I'll be shifting it by 2. So 1, 2. 2 elements I'll shift. So next filter will be applied on next 2. So this is how stride will work. If I have stride 1, so I'll shift it by one value. So this will be working on this area. Then I'll shift again by one value. So it will be working on this area. Shift by 1, shift by 2, shift by 3. That is your stride information basically. So for instance, let us take one example that we are applying max pooling. The name indicates itself. Like I'm applying my first filter on this section. So what is the max value in this particular area? 0.5 will be the max. So first element is 0.5. That is max polling. Means from that filter, whatever is the max value, that will be inserted into the polling result on the grid value. The first grid extracted from the max polling. In case if we are using sum polling, in that case we'll be summing up all the entries from the first filter and the sum of that will be entered here. In case if we have average polling, based on the size of the filter, like here we have 2 cross 2, so accordingly the average will be calculated and the average value will be inserted here. A simple mathematics behind this. So accordingly the name is given. So then we'll put our stride or window right here. And then the next element from here we are getting, since 1.6 is the maximum value from the second level, so that we have updated over here. Similarly, from this also we are updating the max value as 0. Okay, this there may be some mistake. The entry may be missing, so there it will be 0.4 basically. And similarly, for next one also we have a maximum value. There may be some issues with this one. So this will be 1.7. That is your maximum value we are getting from this. So accordingly, based on how we are applying your filters or what kind of polling technique we are applying, that we are updating into the system based on this. And one more, or the last one essential layer that we need to discuss today is your fully connected layer. So on the convolution neural network, we have on the last phase, we have fully connected layer that is going to extract everything from the previous layers, and it is going to help you make single dimensional metrics with the flattened version that we will see in the implementation also, that how we get the flattened version. Tomorrow also I'm going to discuss few additional layers of your CNN. There also we'll talk about this flattened, that how we get it specifically by using the calculations behind. So this will help you to extract the most relevant feature sequences on the final stage to make decision or to predict final label from your pictures. Like if it is 1, 2, or 3, what digit it is, that decision will be made by the final layer. So this fully connected layer means all the neurons are connected layer by layer to next one. So that becomes fully connected layer. We have dense layer also that we call further. So dense layer means when we have dense connections, all the layer elements are connected to each other, and that becomes a dense network on the final stage. So what kind of prediction we are making, what kind of analysis we are making in the data set, accordingly we connect these layers on the basic CNN model. So this is all from the basic theoretical element that we could have discussed about deep learning and CNN. Next, we'll move to implementation also. We'll try to do a minute implementation from this CNN approach. So what I'll do here is I'll add one more notebook. I'll add it in a separate element. So this one I have renamed as session 1 for day 2. One more notebook I'll create here for session 2. All of you can do it side by side. You don't have any dataset for this one, since we'll be getting it from the servers directly. So from the Python libraries directly, we'll be getting your dataset instead of uploading it from our side. So I'm adding here day 2, session 2. And inside this, the very first thing, now again, we are going with the implementation for the CNN based on what I understood.
Madam, one thing is that you using this particular Colab library, or you are using your own Google Drive dataset?
For what, sir?
Madam, in CNN implementations, you are using in dataset, because I already logged into the Google Lab and I'm using one Google Colab file also. But thing is that all the dataset you are sharing, that I uploaded into the file sharing area. But sometimes
Sir,
it
for
will.
this current session, we don't need any dataset to be uploaded separately.
Okay, so I directly connect it to the Google Colab and typing this particular code you are providing.
Yes, yes, yes. No
Okay,
need
madam.
to add any other dataset.
Okay, madam. Thank you.
So the first task I'm adding here again that we already know, we need to import necessary libraries. And there will be several libraries that I need right now for building a CNN. We need a TensorFlow framework and we need Keras interface also. So those also will be taking now along with some basic libraries that include NumPy, the first library we need. And if we have to plot anything in between for that, I'll get matplotlib. Sometime you can use again the other libraries also that we have discussed about, Seaborn or Plotly, etc. So matplotlib.pyplot as PLT I'll get. These two we already know, so we need not to talk much detail in this. Next we have TensorFlow. In my case, I'm able to get it directly, but in your case, if you are not able to load TensorFlow directly, you can do one thing before running this code. You can install your TensorFlow. So pip install TensorFlow, you can write directly and run this command. In my case, I need not to run this command. In your case, if you will not be able to access TensorFlow directly, you can try first this command instead of installing whatever I'm writing here. First, we'll try this. If you get any error with the TensorFlow, then you can run this command before this one in the same pattern that I'm writing here. I'll share this code, so don't worry about that. So from TensorFlow, I'm importing Keras interface. This is just for easy development of your system, and we have several other features also in the Keras interface, so that we are using right here. And then we have again TensorFlow.keras.layers. Now I'm getting some layers. First, we need a sequential layer. That is the most essential layer. We have the input layer in the form of sequential layer right here. Then we'll go to TensorFlow.keras.layers again. Okay, this one I need to change. This is basically models. The type of model I'm using is sequential. Second is the layers I need to get. So import this. First is convolution 2D that we discussed recently. Max pooling 2D that I'll also use. Then one dense layer I'll use. Then I'll use flatten layer. Don't worry about this layer. We'll discuss about these tomorrow also. I'm not just extending theoretical discussion because we have to do implementation also. So leftover part definitely in the tomorrow's theory session we'll discuss. So few layers, few essential layers I have updated over here. And I'll also need one more option over here. One encoder technique I'll need. So for that, I'm taking help from Utilis library, and from here I'll get two categorical for encoding. Yesterday also we have done some encoders on the CSV files. Today we will apply this directly on your uh, target values. So that two categorical I have imported. I'll run this part, and if it works fine, I'll share the code with all of you. Let us see if we are able to get it easily. Since TensorFlow is a heavier model, now your system will take a little bit of time to get things ready. If you are using it on a slow internet, definitely Google Colab may take more time. On Jupyter Notebook, maybe it could be faster if you have a good processor on your system. So this is how we proceed with the deep learning. We need more capacity. If we have a very huge data set, then in case if you are using Google Colab sometime, it will not permit you to execute that on the basic CPU access. Then you may need to get the paid version of TPUs or GPUs from Google, and then you can execute your heavy data sets. Otherwise, you may need to install your Jupyter Notebook on the very high power laptop with a good memory capacity, with a very fast CPU, so that you can execute that huge data set on your and model on your system. So in my case, I'm getting the green tick over here. So it means my TensorFlow is working fine and I need not to install it separately. You all can try it right here. I have inserted all the importing tasks in the session 2 section within the same window. So you can just run it, and if in case it doesn't work, just run this previous command, then then run this again, and everything should work fine. I can share this one also if anyone needs. So in case if the second code doesn't work directly, you can use this first. Otherwise, no need to install that. Let me know if you all are ready up to this. This is the very first thing we are doing.
Madam, kindly share the sweeper code URL because it is not opening.
What is not opening, sir? Code or
Say-
sniper window?
Sweeper window that you are pasting the code that you need, sir, madam. Only just
Okay,
give me the sweeper window code.
so I'm just running it right here. I have inserted it in the chat box. You all can find it there.
It is much more better, madam.
So I'll wait for your responses as soon as you are ready with all the libraries that we need. Thanks for those who are updating continuously in the chat box. And got the green tick, that's good. It means your code is running fine. Now we have load dataset as your second task over here. So this time, as I told you, we'll not be getting any CSV or image dataset folder from our system. Rather, we'll be extracting it directly from the TensorFlow platform, because on the TensorFlow itself, we have plenty of datasets. And since today we are using only a very basic dataset, that is your MNIST digit dataset, so that we are applying here directly. So from TensorFlow itself, for instance, I'll one more thing I'll do here is for importing TensorFlow as TF. I'm giving just a nickname to my TensorFlow so that I need not to write TensorFlow as full version every time. I can use just the nickname TF. So I'm just importing it with a nickname over here. So you can do that. So from this, what I'll get is I'll try to get xtrain and ytrain. This is the version of data set we extract from the system directly. Depending upon how your data set is saved on the system, on the library, accordingly, you can extract it. So what I'm adding here is 4 elements I'll try to get from my data set: xtrain, ytrain, xtest, and ytest. And I just hope that all of you are aware about train and test data. Training dataset we use for model training, testing dataset we use for evaluating model performance, and the X and Y, what these represent? X represents your input features, Y represents your target. So that is the distribution we are having over here. And we are applying here the datasets module, and from datasets module, I'm getting MNIST dataset, and I'm applying load underscore data function directly on MNIST so that I can load this particular data. And then I can use a print command directly to get shape of my data. You can use other ways also. I'm just using a simple technique here. For I in, you can use direct shape commands also. So I'll use this section to iterate through, and I'll put it here directly. Okay, one more thing I'll add here is I'll make it okay, for the iteration I'm updating here one square bracket. Let us see what we get in the outcome of this. uh, okay, this is a typo. Let me just update. We'll be using a for loop over here. Still I have a typo over here. Okay, I need not to close these brackets in between because I have copied it directly. So we'll be extracting this information directly from the elements that we have. Now you can see it took some time to get a data set from the original source that you can see on the Google APIs storage folder. All the data sets from the TensorFlow are saved from where we are getting this information. NPZ is the file type that we generally have with this kind of data sets. And then we have this. This is the size of data we are getting right now. You can see input features are always in the form of a bigger matrix. This is your Y or target dataset for the training with 60,000 rows we can see in the matrix. And then this is your xtrain variable. This is your, test variable. This is your Y test variable. So one by one, shape of all these elements it is describing to us. Now, what we have next, these are basically number of observations in each category, and this is your grid size for pixels for every image that we have inside. So accordingly, the distribution is appearing over here. I'll share this information with all of you so that you can load your data set.
Madam, your code is not updated in the sweeper. Kindly check this one, madam.
Sir,
I already.
everything I'm updating, just give me some time. I'm
Mhm.
updating everything.
Because I already is opening previous code, it is always showing. No, new code is not showing.
Everyone, please just respond in the chat box if you are able to see code in the sniper window or not.
We can see, ma'am. In I think sir is not using DLA underscore this day two sheet.
That may be possible. Sir, we are using this particular sheet. See, DLA underscore day two. And this is the last portion. You may have to scroll down, and I have started here session two. After this, I have updated everything because this is the only screen everyone may be seeing right now, and they are getting code from here only. Otherwise, you can just refresh your this window, and then you may see everything updated on your system. If maybe a case if your internet is slow or anything like that. I'm just getting some responses in the chat. I think yes, all of you can see the code also, and some likes also have seen as responses. Okay, so got the shape info. Thanks for the update, ma'am. So we are ready with the data set on our system. So now maybe if some of you are just curious that how this data set may be appearing in actual, so let us see just a quick info about this if I want to see, because this will be automatically extracted in the form of pixel grids. So for instance, if I want to see this X train, you will see how this dataset appears on the background. See, this is a array size, array structure. And there will be a very bigger matrices like 28 cross 28 matrix we are saying. Na? So that will not be displayed in one go because there is a limit on the system. So accordingly, the middle values are hidden and outer ones are updated here. And now you may see that the outer ones are zero. Majority of these are zero. Can anyone say why we are seeing zeros on this matrix? We have discussed this part just recently. Why we are seeing zeros on the edges over here? Anyone in the chat box? Why not any other value is visible right now?
because that represents the border line, border
Right.
area.
That will be your black color mainly that you will have, and that black we represent with the zeros. So the character, whatever digit is written, that will be somewhere in the middle. So in that area that is hidden here, because we are not seeing the entire matrix over here, so that we are able to not extract exactly from this region. So this will include like 60,000 is your entry counts. Accordingly, there is a very huge size. That is why the inner portion here is also hidden, because we have very huge count. So starting 5 matrices and ending 5 matrices, it is displaying by default. But maybe if we want to see just one matrix precisely, so I'll add here element 1. So maybe the first one only I want to see. So I'll just run this. Let us see what we get in the outcome. So it says first element is 0. This you can see a small image right here. And it says this array is a 28 cross 28 array. And now if you want to see data, that is also a very creative feature we have over here. How this 0 is being represented inside this 28 cross 28 matrix, we can just click on show data and you can see the matrix over here, although you cannot understand it so easily because this is on the next line also it is updated, like from here to here, just because the size is big. So that is why it is on multiple lines, because your Google Colab has certain capacity how big matrix it can display in one go. So to this this is first row of your matrix, then this to this is second row of your matrix. So borderline elements you can see they are zeros. Then if you go to the middle, so accordingly how this 2 is displayed, accordingly some values are there. So this will be updated. So this sequence currently they are following with 0 to 255. So that is being updated. The maximum element value you will see 255. The minimum we are seeing 0. So you can see some darker, some whiter regions for that print. You can see. If I hide this, you can see the zeros are with the whiter and remaining things are with the darker. So accordingly, those values are updated in the matrix to visualize this particular element. If you want to see any other like second element, I can test that also. So it says second element, second figure in our list is 4. So if you want to
Ma'am,
see data, that is also visible. Yes, please.
Upma ma'am has raised his her hand.
Okay, just let me know, ma'am, if we have anything to discuss.
No, ma'am. No, ma'am.
Okay.
Thank you.
Okay, thank you very much. So I'll just hide this data because this is a bigger matrix. All of you can try this with different elements just to see how your image is appearing. So this is a quick way to see your image. We can also use this with the plotting task also. If you want to see an image on the large scale, that also we can do. I request you all to kindly mute yourself. A humble request to all of you. If you don't have anything to discuss, kindly mute yourself. So for instance, I'll just plot one sample image. For that, what I'll do here is, for instance, I'll first choose my image index 0 that we have also used here also. We can use index, such as I have used index 1, index 2, etc. So I'll choose image index 0, for example. Then I'll add, this is just one plotting technique. Some people were asking that what kind of plotting we can use on image data. So this is a kind of plot you can use on that. So image index of xtrain I'm updating. We can update it here also directly like I have done in the previous code. That is also possible. That is just different things you can apply on the system. Then plot the image, I'll write here. At that, since I have already imported matplotlib right here, so that sequence I'm taking here from matplotlib. I am show function we use for images generally. So image I'll use CMap, the color map. Basically I'll use gray. You can use different color maps if you want to see colored images. That is also possible. Currently I'm using the basic one, gray color map only. So title I'll update over here, and inside title I'll add, for instance, the first element will be label, and after this the next element will be auto updated. So that will be from y train, for example, and image underscore index. This is very simple to understand what we are doing here. For instance, first I'll update my image from X train dataset, and the respective label I'll get from Y train. I hope you can all understand this. This is same as what we have done in your CSV files. On the first observation, there will be a Y element, or there will be a target element linked to those observations. So the same thing we are doing here, because currently we have labels and features in separate datasets. So first I'm extracting the X dataset for plotting the image, and on the top of that I want to put title with label value of that same image index. So that we are doing here. Ultimately I'll use plot show, and let us see what we get in the output. So I'll just run this part and we'll see the image. So this says label 5 we are getting, and this is an image because this is a handwritten dataset. So people may have written it in different ways. So this is one kind of image we are getting. So all of you can try with different index values also. You will be able to get some plot out of that. Let me know if we are all ready up to this.
No, madam, code is not showing because if you state the code in the chat box, it is okay, because in Snapchat, it is always giving the same previous code in your diabetes part.
Sir, I can
I always
understand.
open the URL you are giving, that URL opening, it is always showing the same thing on diabetes and as well as the previous code you are just completed, previous session. So if you pasted in the code in your chat box in here, I directly pasted and done the code.
Sir, are you able to scroll on this window?
Then in
Okay, so I'm not sure what is happening on
It
the.
is showing, ma'am. I think there is a problem over there.
Okay, so still, if you want to
I
implement.
always scrolling, but it is not giving me the authority to go next one. It is
Okay,
stop on the
so
last word.
I'm updating everything in the chat box for you. You can try from there.
Yes, madam. It just suit. I check out.
Yes, you can do it easily now.
Yes. Thank you.
So we have just received one sample image, and next to this what we will do is we will use one operation over here to normalize that image, because initially what we are doing is we are applying your element wise information with that 0 to 255 element. So I'm just using one simple normalization technique over here. There are different normalization technique. Again, I'm mentioning, I'm just using one random technique over here. Normalize the images. So that will be with the input features. I'll be doing this operation. So train images I'll get in the outcome, and test images also I'll get in the outcome. So on the train images, definitely I'll process xtrain divided by 255 is my final element to which I need to process, and I'll just use minus 0 0.5. This is one way of normalization I'm using. We can normalize it with different values as per our requirements. So just one factor I'm updating here. Same I'll update for the test also. On the lower scale, basically, I'm bringing it. Yesterday, we have discussed variety of normalization techniques. Just one among those we are using over here. So after this, we are getting your updated normalized dataset in these variables. So I'll share this one also. We have this on the snipper window and also on the chat window. So after normalizing your dataset, the next part I'll be doing here is reshaping my images. One more element, I'll be reshaping my images, because whenever we are updating a filled data set, sometimes what happens is all your images are not available with standard dimensions. So sometimes we have to reshape images. Again, there are so many ways to reshape images. Sometimes we give manual shape elements, sometimes we take help from some functions. Several processes are possible. In our case, I'm going to use a function directly. Since we have lesser time available, I'll not be creating a specific function for this. Rather, I'll use an inbuilt function for this. Reshape images, that is the task I'm updating here. So for train images as well as for test images, both of them I'll be updating right here. So what I'll use is from NumPy, I'll use directly expand dimensions, that is my function. And inside this, I'll use train images x is equal to 3. On all 3 x's, I'm going to expand this
Madam,
because,
why you multiply divided by 255? It is the pixel intensity is making 0.
sir, we are also adding one more element further.
That is clear, but why you divide by 255? It is pixel intensity is 1, you are divided by extend this value, or
So
you making
you see here in the
Mhm.
image itself, the maximum element value we have is 255.
Yes, yes,
So
yes.
generally, the representation we use from 0 to 255, that is
Hmm.
total 256 pixel element values from the
Hmm.
darker level to the brighter level. So
Hmm.
the maximum element I'm using here for the normalization purpose.
Okay, okay.
Yes. So next I'm reshaping my both train and test images right here. So I'll be just updating this reshape information, and I'm sharing it here with all of you as well. So these are some initial normalization and reshaping that is a part of data pre-processing that we have used in your machine learning part also. Means initially we have learned this. Sometime we have to apply some initial pre-processing techniques on image data sets also. Just very basic that we have seeing here. Similar kind of different elements you may have to apply on basic normalization just to enhance your outcome of the deep learning model. Even if you apply directly, sometimes models will work, there will be no issue, but the quality of outcome will be less in some cases if the image information in the beginning is not clear enough. So we generally prefer to apply some pre-processing elements in the beginning. Next task that I'll do here is, since I'm not going to do here a very in-depth processing, rather I'll be doing very basic elements only since we have lesser time. So what I'll do here is train test split I'll do directly. Train test split, okay, I'll do basically validation split because this test we already have. So train validation split I'll do, because I'll divide my data into 3 sections. We can do in 2 sections also, that is also possible. We can directly do with xtrain and xtest only. But in my case, what I'll do is, first I'll use xtrain dataset to train my model, then I'll use xvalidate dataset to validate my model performance. And then X test dataset I'll use as a totally unseen data for my model that I'll use for final predictions, that how good is my data on a completely unseen dataset. So that basically I'm doing here. So what I'll do here is train validation split. And for this, we'll use a function that we have discussed yesterday among your random sampling also. If someone can recall it, I think it is a train test split function that we have discussed yesterday. And I have also answered someone's query who were asking that why we are using a underscore after sample while extracting that train test element. Now today I'll show what we were hiding inside that underscore. There were remaining elements of the outcome of this train test split. So what we are doing here right now, for instance, I'll write here first element I'll get is x train, and second element I'll get is x well, third element will get y train. So this is a specific sequence we follow with your data outcome from train test split. First it will bring you the feature sequences, then it will bring you the target sequences for train test or train validation. So this, the function name itself is train test split, although we can use it for different type of splitting. Here we are using it for splitting between training and validation dataset. So we are getting 4 elements. What we were doing yesterday, this we were calling sample, and all these 3 we were holding behind by using that underscore directly, because we were not looking forward for all the elements extracted by the train test split over there. We were rather interested in the first element only. So today we are updating all these informations over here. And then I need to apply my function on the other side of the equation. And here I'll be updating my information on train images. Why? Because I'll be extracting my train and validation dataset from original training dataset. This is the general procedure we use for extracting validation dataset. Validation dataset is always extracted from the main training dataset. That validation dataset is always a part of training dataset, and testing dataset is always from a separate section. That is a totally unseen data for the model, we call it. The second element is y train. This is your target, this is your feature sequence. And then we'll update here test size. You can update either train size or test size, anything is possible. So for instance, I'm using 30% data for the testing purpose, or precisely we can have it for the validation purpose basically, but the parameter name inside function is test size. So don't get confused about that. Just the function name and function parameter names we are using as it is, but ultimate extraction we are doing for the validation dataset. And what percentage I'm using for that? 30% I'll use as a validation dataset, and 70% I'll use as my training dataset from this. And after this, I'll update shape of my this extracted data. For instance, I'll just hover over this sequence. So what I'll do is simply I'll get this sequence. So for I in all of these, or I can even add X test or X images. So that is your test images and Y test. All the elements we can test all together. Inside this, I'll use print I dot shape. There are many ways to do same things. I'm just using one example over here. So I'll run this part. So these are my different shapes right now. This is my X train. This is my X well. This is my Y train. This is my Y well. This is my test, or we can say X test images. And then this is my Y test. So these are different element sizes right now I'm having. Majority of dataset goes into the training side. Secondary level is on the validation side, and the minority dataset goes into the test size. There is one important factor that we need to understand over here. Whenever we are doing this splitting task, if you run your model time and again over these codes, every time different number of elements will be splitted, because there is always a random shuffling. So when you run this code again, maybe some images will go into train, some will go to validation. Accordingly, if you rerun, some other shuffling will happen between images and they will move here and there. If you want a constant result every time, although with random shuffling, but still whenever you run this code, a constant result should arrive. So for that, we insert a random seed into the execution. So for that, for instance, I'll add here a random seed, and there is no specific value for this random seed. Basically, any number you can apply. There is no specific significance of number over here. We apply any number like 2, 8, 10, anything you can apply, just to fix the elements, that every time we run this code, same results will be updated, so that your model performance is updated on the same level, instead of getting every time a new shuffle of data set. So this I can run over here, and every time we will be getting okay, just let me see. Okay, because I have already run this code, so it will not work directly. I may need to refresh. Just let me refresh it again, because I made a little change into already extracted elements, and that will not be updated into the system immediately. So I have to rerun it. So this I'm getting. I'll share this code with all of you right here. So you can execute this and see how your train test split is working. Let me know when we are all ready up to this.
Ma'am, there is a question in chat. Why we need image normalization by Vivek Kumar?
Okay, fine. Sir, just let me show you one thing in the outcome of the signal that we are getting here that will help you to understand the difference. I'll run this part here, and for instance, we have train underscore images. And I'll just try to get a first element of this. After running this part, I'll just execute this. See, now what we have in the output, I think you will be able to compare. This is based on what we have discussed yesterday. What we are trying to do here is we are bringing everything to a smaller scale. The original scale of your this matrix was 0 to 255. Now I'm bringing everything to a smaller scale. You can see, because I have used a minus 0.5. I told you that you can have any value based on your requirements, or some random values also we try sometime. So all the zeros automatically will be updated with minus 0.5. That is the mapping that we have understood yesterday. And the higher scale values automatically get with this. So how we are reducing scale of your matrix, that we are understanding here. We are bringing everything to a lower scale, like maybe from minus 5 to a maximum value that may be possible with the divide by 255 factor. I hope this is clear. This is same.
Excuse me, madam.
Yesterday.
Madam,
Yes, please.
excuse me, please.
Yes,
Can we
please.
correlate this particular with the that by means of normalizing in future the computations will be also reduced. Number of CPU cycles also will be less required. Can we say like that?
Sir, this is not about CPU cycles directly, but yes, the complexity of the computation we are trying to reduce over here.
All right.
Yes. So
Ma'am,
we
there is another question.
uh,
Mansi,
okay, we are setting the validation sample size, train test we have mentioned. Okay, this I just explained, but no problem, I'll explain it again. Ma'am, see what we are doing here. Train test split is the name of the function, and test size or train size is a by default parameter of this function. However, here we are using it for extracting validation data set. So even if inside this I'm using the parameter name is train size, consider this parameter name only. Don't link it to the outcome right here. This is just parameter name. So idea is, for the secondary extraction, secondary split that I'm having, it should be 30%. So whatever I'm using as a secondary split over here, that will be automatically 30%. So even if it is a test value, whether it is a validation value, this is just the percentage we are deciding over here. So if you are using it between train and test, then it will be applied to test. If you are using it between train and validation, it will be automatically applied to validation. This will directly link with the variable names over here, and accordingly the percentage will be applied. I hope this is clear. Okay, thank you very much for the update. So we are here ready with the train test split. And now we will move to the next part, that is to set up your model for this particular thing. So let us build model first. We'll not apply dataset directly. We first build model in CNN structures. So what I'll do here is I'll update few random details inside it. For instance, number of filters inside my this convolution, I'll update 8. There are some random values I'm updating for the layers. Filter size I'll have is equal to 3, for instance. Filter size I'm updating is 3, and then pool size. These parameters you can use by default also. If you don't apply them, then also your system will work. But I'm using some parameters over here. For instance, then I'll be building my model, and inside this, I'll be using here sequential model. So inside this, I'll be passing all my layers one by one. So here I'll be updating them. First layer I'm updating is convolution 2D that we have discussed already. Only those layers I'm updating here. So the number of filters for the convolution layer I have already decided. Then filter size I have decided. Then input shape also I'll mark. For example, input shape I'll try to pass is 28 cross 28 is my matrix size, and grayscale image I'll pass. So 1, I'll add a parameter as a here. Next, max pooling layer that we have already discussed. Max pooling 2D I'm using over here. These are the layer names basically that are saved inside. Pool size we have already used here too. So this basically how your system will stride through this. So that will add over here. Either you can add the value over there, or you can mention it earlier and update it accordingly. Both options are there. So here we need to pass the parameter like this. After this, I'll use one flatten layer. About this layer, we'll discuss tomorrow also in detail, so don't worry about it because we had lesser time for the theoretical discussions today. So no, don't worry. I'll disclose everything about this layer tomorrow. So next we have is activation. So final activation function, I'm using softmax over here. So generally, most of the time in your CNN models or majority of your deep learning models, the final activation function we use is softmax. I'll discuss more about this tomorrow also. By default, in the previous layers, the activation function is relu that we have discussed. We can apply it by making adjustments also. We can make some changes also into the system settings. And on the final layer, we generally apply a softmax, that is your output activation function in majority of cases. So this is a basic model I have added with only few layers of abstractions over here based on what is essential for my this particular modeling. So you can see this model must be ready. It will just display this information that from the packages we have updated every information that is required to build this particular model. So I have inserted this information on your can we use already splitted data set as train and test in separate folder? Yes, that is also possible. Since currently we are getting data set from the online sources directly. So that is why we are using it like this. Otherwise, you can have it in your folder and you can get it same as your read sequences from there, and you can start using that. That you can do definitely. If it is already in the folder, that also you can do. So first we are building our model. Then we will be compiling this model. There are two different stages we apply on these deep learning models. First, we build a model by applying different layers, and then we will compile this particular model. Compile your model, and for that, what we do is model.compile command we will execute over here. Inside this, I'll update first of all my optimizer. About these optimizers also, I think we'll discuss on Friday. We have a detailed discussion about optimizers. So currently I'm using one default optimizer here as ADAM. Detailed information about these we are going to discuss in upcoming sessions. So don't worry if you are not aware of this. We'll definitely discuss this further, since we have some limited things possible to discuss in every session. So few things will definitely come across in coming sessions. So one loss parameter I'm using is categorical cross entropy. There are variety of loss parameters you can use. Sometimes we use sparse cross entropy. Sometimes we use categorical cross entropy. These are based on what type of image sequences we have, how your target data sets are updated, how your input features are updated. Based on that, we try different loss functions. Like in case of your simple machine learning models, loss parameters may be like simple MSC, RMSC, etc. In your deep learning models, we have entropy based informations. So categorical cross entropy is one of the most commonly used loss function. Then the target metrics will use, since this is a classification model that we are building with digit classification, we'll use metrics accuracy as our target parameter over here. So these are the essential parameters that we will pass. And let us get a quick model summary also right here. So whatever we are designing, that summary we'll try to get. So this is currently my model sequential, and these are the layers I have updated. These parameters are updated automatically based on what settings by default we are following. So that will be done automatically. You need not to worry about this. On advanced level, currently we are learning it on the beginner level. Later on, you can update these values also. You can use some hyperparameter tunings, etc., to adjust parameters inside your models. But currently we are not discussing that part. So as a beginner level, you can just use the default values right from there. So this is your model structure right now that we have from the system. Now we come to the third phase of model building, that is your model training. So I'm updating here, train your model. So train the model, I'm updating as a task right here, and we get updates of your training model into the history variable that we can utilize further for any kind of graphical analysis. And I'll just fit my model, and fitting we always do on the training data set. And I have imported one function to categorical earlier, so that I'm using here to convert my target variable into a categorical information specifically. So xtrain variable, if we try to see this maybe at initial level like we have it here, let us see how it appears. Y underscore train, and if I want to see its first element, it is currently in this form, like normal decimal values we have. If I check other element, this is 6. You can see this is normal digits we have. So what we are doing here, we are applying a categorical update for this. Like it will be represented with a specific sequence of digits. Like for zeros, it may be updating 00000. Like 8-bit sequence, sometimes we use 4-bit sequence. By default, it will start with, I think, specific like 8-bit sequence, most probably. So we can check that later also. So like for 1, it will be representing 0000 and 1 at the final. So accordingly, it will be decoding everything into zeros and ones of sequence. So that categorical contribution or categorical conversion we need before deploying your model. So that we are updating right here. After
Then
this,
what is the purpose of last column 13 6 110? What is the purpose of this one?
sir, which one?
Total parameters 13610. What will basically giving this for a particular value? This
Sir,
last one, madam.
this
Yes.
is your dense layer, although we'll be discussing it tomorrow also. These are
Okay.
basically how many connections we are following inside a dense layer, because as the number of neurons grow inside, accordingly, a number of connections will be formed inside. And accordingly, the data will be processed inside those connections.
So, madam, 64, 32, 8, and 4. These why you are making the, connections, or it is automatically by default connection, whatever may be the neurons you
Sir,
are applying.
based on the default settings of the dense layer, you can see here, if we observe, only this neuron value I have given 10. No other parameter I have added. So everything it may be taking with the default settings right now. If we
Okay,
update
okay,
other parameters of the dense, then accordingly it will be evaluated further.
okay, okay.
Yes. So next we have the validation data we have to update into the model for side by side validation testing, or we can say evaluation of the model. And here also categorical data set with y, well, I'll be updating. And after this, yes, this is my final variable. So a comma may or may not be required over here. That is just an essential bracket closing sequence I have updated. And now, since I have updated 25 epochs, you can try even with the smaller value. This, depending upon how big is your data set, this may take some time. In the meanwhile, you all can run so that we can see the outcomes. So I'll just share it right here for all of you. You can run your model behind. In the meanwhile, let us see what outcome we get, depending upon how big. I should have run it with the smaller epochs, but let us see how much time it takes. In the meanwhile, I'll just update one more sequence further, just to see the outcome of our model while we run it.
Madam,
Yes.
kindly share it in the chat box, madam, chat box.
Okay, I'll just update. Yes, sir, you can find it in the chat box now. So we have just trained this model, and while it is updating, I'll try to show you the accuracy values on the test dataset as well. So let me see here. Evaluate on test data, for example. That is totally unseen data for your model. So I'll get test loss as an outcome and test accuracy as an outcome. Two things I'll try to evaluate out of this. So model evaluate function I'll use directly. So inside this, I'll pass test images, and again to categorical, I'll update y underscore test right here. And let
Loss will be decreased by each epoch or automatically constant in a particular
sir,
cases.
your voice is not audible. Can you please repeat?
Madam, in case of accuracy and loss is always decreased in each cases, or
Yes.
it will be
Loss
constant.
we need towards 0 is better.
Mhm.
Accuracy towards 1 or towards 100 is better.
Okay.
So here I'm updating test accuracy. These are my parameters. Let us see what accuracy level we get on the test data set. Depending upon this, we can make predictions also. If time permits, we can see this on the real data sets. Otherwise, don't worry, because this same thing I'll be using for one more comparison later on. So the outcome of your model, you can see here, the accuracy on the trained data set we can see is 99% almost. That is good enough. But on the validation set, we can see this is 97%. So a margin we can see on the validation and on the training data set. However, when we test it on the test data set, again, the accuracy is around 97%. So what happens sometime when we evaluate our models, we try to rely on the training accuracy. But actual thing is in your test accuracy. This is the actual thing that you have to evaluate for goodness of your model. How well you have created a model, that will depend on how good is test accuracy. Because sometimes your models overfit. You will have good accuracy on the training data set, but a bad accuracy on the test data set. And whatever we are doing here, whatever changes we are seeing here, or whatever updates or whatever differences we are seeing in both levels of accuracy, that also we can fill up by using additional parameters further. So in coming sessions, we'll come to that part also, that how by using some specific techniques we try to reduce this margin between training accuracy and test accuracy. So that also we will learn further. There are different techniques to do that. So initially we are just learning one basic, because this was our first session on the CN deployment on the real-time data set.